All right, listeners, welcome back to another TalkTensors Deep Dive.
Yeah, thanks for having me back.
So for this deep dive, we're going to be looking at something very cool.
Yeah, very interesting paper.
Called Spatial Distillation-based Distribution Alignment for Cross-Headset EEG Classification.
It's a mouthful.
It is a mouthful, but it's going to be good. I promise.
It's a good one.
So, for those of you out there really getting into machine learning, especially for like brain-computer interfaces.
Yeah, BCIs.
One of the things that you just constantly run into is that
The headsets.
Yeah. The different headsets.
You've got like this Tower of Babel situation with all these different EEG headsets.
Or EEG headsets.
With all these different models, each with their own specific setup.
Right.
And it makes it a real pain to try to combine data or apply findings across them.
Exactly.
You train a great model on one headset.
Yeah.
And then it's basically useless on data from a slightly different one.
Right. And that's...
But that's the problem. That is exactly the problem that this paper is addressing.
Exactly.
And they're offering a very interesting approach to solve it.
Yeah.
So for anyone who is serious about making BCI technology more widely applicable and less reliant on specific hardware, this is worth a look.
So let's jump right into it. So the core problem here is that, as I'm sure all of you know, that work with BCI data, is that,
the headsets are different.
The headsets are different.
Like the number of electrodes, their placement on the scalp. These variations create data sets that are fundamentally incompatible with each other.
Yeah, it's like trying to fit puzzle pieces from completely different puzzles together.
Yeah, that's a great analogy. So it's like you're building a model to recognize objects, and you're using a smartphone camera, and then you try to feed it images from a specialized medical imaging device with completely different pixel resolution and color depth. It's not going to work. Similarly, if you have an algorithm that's trained on the rich spatial information from a 64-electrode EEG system, it doesn't know how to interpret the sparse data coming from a 16-electrode device.
Right.
Like the information is just not there.
And so what a lot of people end up having to do is just throwing away that extra data from the more detailed headset to match the lowest common denominator.
Exactly.
Which is so frustrating because you're losing valuable spatial information.
It is.
So, we've got this very long title, Spatial Distillation-based Distribution Alignment for Cross-Headset EEG Classification.
Yeah.
So let's try to break that down a little bit.
Okay.
Spatial distillation sounds like it's some way to capture the essential spatial information from a richer data set. Even when you're working with one that isn't quite as dense.
Right.
And distribution alignment suggests that there's some method to make the data from the different headsets to make their statistical characteristics more similar. So essentially what we're saying is that SDDA, this new approach, is trying to learn those underlying spatial patterns and normalize the data distribution. So that models can generalize better across different hardware.
Exactly.
So, and the interesting thing is that a lot of the previous work in transfer learning for BCI has concentrated on just adapting models across different individuals.
Yeah, like cross-subject or
across different recording sessions.
Yeah, cross-session.
But using the same headset.
Right.
So the fundamental structure of the input data, the electrode configuration, remains the same.
Exactly.
But what SDDA is doing is it's addressing this much more challenging scenario.
Way more challenging.
Of heterogeneous transfer learning.
Yeah.
Where the input space itself is different.
Right.
Which is a much more practical problem to solve.
That is a huge problem.
Because, all these different EEG devices available.
There are tons of them.
So how does SDDA actually achieve this? Like, what are the nuts and bolts here?
Okay, so it really hinges on those two main components in its name. Spatial distillation and distribution alignment.
Okay.
So SD and DA.
Right.
So let's start with spatial distillation.
Okay.
Think of it like you have a more experienced chef who has tasted a ton of variations of a dish and understands its fundamental flavor profile. And they're teaching a less experienced chef how to capture that essence, even if they don't have access to the exact same ingredients or tools.
Okay.
So in SDDA, we have this teacher model that's trained on data from a headset with a full set of electrodes. So it has this rich understanding of the spatial patterns of brain activity.
Okay.
And then we have a student model.
Okay.
It's trained on data from the same source.
Okay.
But using only the subset of channels that are also present in the target headset.
Right. So the one with fewer electrodes.
Right.
So the teacher have the full picture.
Full sensory input.
And the student's working with like a reduced set.
Reduced set.
So how does the student actually learn
right.
that richer understanding from the teacher?
So that's where knowledge distillation comes in.
Okay.
So the teacher model, having learned from the more complete data, develops a more refined understanding of the relationships in those brain signals.
Okay.
And the student model tries to mimic the output of the teacher model.
Okay.
So specifically the differences in the probability distributions.
Okay.
It generates for different classes, like, for example, different motor imagery tasks. So even though the student is working with less direct spatial information, it learns to make predictions that align with the more informed teacher.
Okay.
So it's capturing the higher level, more abstract features of the EEG signals, even with fewer channels.
Okay. So almost like the what and the why from the teacher.
Yeah, exactly.
Even with fewer direct inputs.
Exactly.
So that's spatial distillation.
Yeah.
Dealing with the different input spaces. So then how does distribution alignment further help in making the data comparable?
Right. So even after this spatial distillation process, there can still be some noticeable differences in the statistical characteristics of the data coming from the source and target headsets.
Okay.
So distribution alignment has 3 components that are designed to address these remaining discrepancies.
So it's kind of like 3 alignment strategies.
3 alignment strategies.
Okay.
So what are they?
Okay. So the first step is what they call Session-wise Euclidean Alignment.
Okay.
Or EA.
EA.
As you know, EEG data fluctuates over time and across different recording sessions.
Right.
So EA is a pre-processing step that normalizes the data on a session-by-session basis.
Okay.
So it basically calculates the average relationship between the different EEG channels.
Okay.
The covariance matrix.
Okay.
Within a recording session, and then transforms the data to have a more standardized relationship.
Okay.
So think of it like calibrating different measurement tools before you start an experiment.
Right. To make sure they're all reporting on a similar scale.
Okay.
And for your machine learning algorithms, this reduces variability in the input data across sessions and individuals and makes it easier to learn consistent patterns, regardless of who or when the data was collected.
So it's like a normalization step.
Yes.
At the data level.
At the initial data level, yes.
Okay, so what's the second alignment strategy?
Right. So the second part focuses on what we call the feature space, which are those abstract representations of the EEG data that the model learns after its initial processing layers.
Right.
So they use a technique called Multi-kernel Maximum Mean Discrepancy, or MKMMD.
MKMMD.
And even after we've aligned the raw input data with EA, the way the student model represents that data internally might still be different from how a model trained directly on the target headset's data would represent it. So MKMMD is a way to measure and minimize those differences. So it tries to align the distributions of these learned features in multiple different ways using different kernels. And this makes the internal representations more compatible across the source and target domains.
So we've aligned the raw data and then how the model internally represents it.
Yeah.
So what's the third part of distribution alignment?
So the third part looks at the output space. The actual predictions the model makes. And they use something called confusion loss, or CL.
Confusion loss.
CL. And this reduces any remaining class-level discrepancies by minimizing uncertainty in the target domain's predictions. So imagine the model is trying to classify different types of brain activity. But for the target headset data, it's often unsure between 2 similar classes. Confusion loss penalizes the model for these uncertain predictions, encouraging it to make more confident and accurate distinctions, even with the characteristics of the target headset data being a bit different.
So essentially what we've got here is we train a teacher on the full electrode data. And then we use that knowledge to guide a student that's trained on a subset of channels.
That's right.
And then we align the input data, the learned features, and the final predictions between the source and target setup.
Exactly.
It sounds like a very comprehensive approach.
It is.
So how do they test it?
Well, they did a very thorough evaluation. They used 6 publicly available EEG datasets from the MOABB benchmark. Which is a standard resource in the field.
Cool.
These datasets covered 2 common BCI paradigms. Motor imagery, where subjects imagine movements. And P300, which is the brain responses to specific visual or auditory stimuli. So they tested SDDA in 2 realistic BCI application scenarios.
Okay.
One was an offline, unsupervised domain adaptation setting where they had access to unlabeled data from the target headset during training. And the other was an online supervised domain adaptation setting where they only had a very small amount of labeled data from the target headset available, which is a very realistic scenario.
It is a very realistic scenario.
For real-world applications, you don't always have a ton of labeled data from your target. So how well did SDDA do? It did really well.
That's awesome.
The paper shows that SDDA consistently achieved the best average performance across all of the tested scenarios and data sets.
Nice.
And it outperformed 10 other established transfer learning algorithms that are commonly used in BCI research.
So this is against a good selection of existing techniques.
Yeah, it really is.
Okay.
So this included some well-known methods like eGinette, DANN, and DANN. They used standard performance metrics for each paradigm, accuracy for motor imagery tasks, and AUC for P300 tasks, which is the area under the RAC curve, because P300 tasks often have imbalanced class distributions. And so the fact that SDDA consistently came out on top across these different data sets and adaptation settings suggests it's a very robust and effective approach.
That's really cool.
Yeah.
Did they try to figure out like which parts of SDDA were contributing the most to that improvement?
They did.
Okay.
They did what are called ablation studies.
Okay.
Where they systematically removed each component of SDDA.
Okay.
The spatial distillation, the Euclidean alignment, and the confusion loss.
Okay.
And looked at how performance changed.
Right.
And these studies showed that each component contributed to the overall improvement.
Okay.
And that combining all 3 elements in the complete SDDA framework was really the most effective.
Makes sense.
They also used this visualization technique called TSNE.
Okay.
To show that the Euclidean alignment step was actually effective at making EEG data from different subjects look more similar.
Okay, cool.
Which is exactly what it's supposed to do. And they also compared SDDA to methods that only use the common subset of channels between the source and target headsets. So they were basically treating it as a simpler, homogeneous transfer learning problem.
Okay.
And SDDA, by leveraging that extra spatial information from the source domain through spatial distillation, performs significantly better in those comparisons.
Very cool.
Yeah, it's really nice work.
So the key takeaway, I guess, for all of us out there working with BCI data is that,
there's a better way.
There's a better way now to train models that can just be applied across different EEG headset models.
Exactly.
Which is huge because,
it's a big problem.
It's a big problem.
That's been holding us back.
That's been holding back the field.
Yeah.
So, by leveraging richer spatial information and carefully aligning those data distributions
at multiple levels.
It's overcoming this major practical bottleneck in the field.
Exactly.
So it's really exciting.
It's really cool work.
Yeah, so this could really accelerate the development and deployment of these BCI applications.
Yeah, absolutely.
Like imagine if algorithms developed on large, diverse data sets. Collected with, expensive research-grade equipment. Could be more easily adapted to data from like more affordable consumer grade devices.
Exactly.
Like that would be a huge game changer.
Yeah, it would really democratize access to BCI technology and foster innovation across a wider range of applications.
So this has been a really interesting deep dive.
It's really cool stuff.
Into the SDDA method.
Yeah.
And now for our novel notions section. We're going to talk about some possible future directions for research.
I love this section.
Me too, it's my favorite.
Yeah, so building on SDDA's success in bridging the gap between different EEG headset configurations, one area to explore would be what I would call like dynamic spatial distillation. So the current SDDA framework does the distillation process as a one-time training step.
Okay.
But imagine a system where the teacher model, maybe it resides in the cloud, and it has access to a constantly growing pool of diverse, high-quality EEG data. So it could constantly refine its understanding of the neural correlates. And this refined knowledge could then be distilled to individual student models that are running on users' personal BCI devices. So it would adapt in real time to the specific characteristics of their current headset.
So the BCI is essentially learning and adapting with you.
Exactly.
As you go.
As you use it.
So what would be some of the benefits of that? Of that kind of dynamic approach?
Well, firstly, it would really leverage the power of continuous learning. So as the central teacher model encounters more data, potentially from higher fidelity devices, its understanding of the underlying brain signals would become more robust and more generalizable. Secondly, it would give users greater flexibility. So they wouldn't be tied to a single headset model. They could switch devices, and the system would just adapt to that new hardware. And thirdly, this continuous distillation could even help to mitigate issues like temporary sensor drift or poor electrode contact in those lower-end devices by relying more on the distilled knowledge from the higher fidelity data.
So essentially, you've got a more resilient system.
A more resilient system.
That's more user-friendly and ultimately more powerful.
Exactly.
Very cool.
So that's one direction.
Okay, so what's another potential avenue for research that you think this SDDA work sparks?
Another interesting direction would be to investigate cross-paradigm spatial knowledge transfer. So the SDDA research focused on transferring knowledge across different headsets, but within the same BCI paradigm, like motor imagery. But what if we could use the information learned from one type of brain activity, like from attention-based tasks recorded with a high-density EEG system, to improve the performance of a model for a different type of brain activity, like emotion recognition, using a lower channel headset. So while the specific neural signatures for attention and emotion are different, there might be some fundamental underlying spatial characteristics of brain activity that are more generalizable.
So essentially what you're suggesting is we could transfer learning not just across different hardware, but across fundamentally different types of cognitive tasks that are being measured.
That's exactly right.
That's a very cool idea.
It is very cool.
So a teacher model trained on a spatially rich data set from one paradigm could distill these generalizable spatial feature representations that could then be used to bootstrap the learning process for a student model focused on a different paradigm, but operating with fewer channels,
That's really neat.
And this would be super valuable for developing BCIs for novel applications where, you know, large, high-density data sets are scarce. It's a more ambitious challenge.
It sounds like it.
But the potential for synergistic learning is very exciting.
Yeah, like imagine if you could use insights from research on cognitive control to accelerate the development of tools for like mental health monitoring.
Exactly.
That's a really cool idea.
That would be huge.
So there's just some really neat directions that this SDDA work could lead us.
Yeah, I'm really excited to see where it goes.
Yeah, dynamic spatial distillation and cross-paradigm spatial knowledge transfer.
It's all very exciting.
All very cool stuff.
And it really points toward a future where BCI technology is much more adaptable, intelligent, and broadly applicable. It is important to remember that these are still speculative directions, pushing the boundaries of what's currently possible.
But as the work on SDDA shows,
the field of BCI is really evolving quickly. So if you want to learn more about SDDA, the link to the paper is below.
Check it out. It's really interesting work.
So thanks for joining us for this deep dive.
Thanks for having me.
See you next time.
See you.